Now, the two black holes orbit around each other and they're coalescing, they're approaching each other. And the deformations in the space-time metric are going to be significant. And that's the reason why we're going to slow down the simulation. Now it begins to slow down. The deformations in space-time metric are significant to the point that we're going to stop the simulation. So at the end you see what kind of deformation occurred. Keeps going. Done. The production of the third black hole. But now the simulation pans, zooms out, and you see these ripples. And these ripples propagate throughout space as gravitational waves. By the way, those ripples have a signature, the signature of the event that caused them. Just like we throw, a rock in the middle of a pond, you generate ripples. The way that the rock landed, the ripples depend on the way that the rock landed in the pond, and so on and so forth. Same thing with gravitational waves. All right, what happens if a gravitational wave passes? We are inundated by gravitational waves all the time. Okay, and so whenever a gravitational wave passes, okay, this vastly exaggerated. Okay, so you have the wave fronts for the gravitational wave coming on one side. And they have the property of stretching things and compressing things at the same time. They stretch it on one axis, compress things. So things begin to move relative to each other. So in the end, if you will, the Earth wobbles. But this is vastly exaggerated. It doesn't wobble by this much, okay? But it does wobble. Well, by how much do we have that event in September 14, 2015? Was truly, in terms of gravitational waves, was truly very, very, very loud. Okay, how big was this event? Well, here there's a little toy simulation, and it's a representation of the hydrogen atom, the simplest of atoms. You have an electron orbiting around the nucleus. How big was that event? Turns out to be 4 times 10 to the negative 18 meters. Okay, that's how big. Okay, that was the loudest event that we ever heard. The loudest event. For us, we were expecting signals much lower than this. Okay, and so we were preparing, bracing ourselves for something not as loud. But we received this. It was so loud, our machines went crazy, essentially. 4 times 10 to the negative 18 meters. That's a small number. It's a crazy number. It's a crazy number. And that was actually, honestly, going back to this guy here, it's actually 4 times 10 to the negative, I think, is the peak. It's because it's a wave. It was like the highest number that we ever registered over there was 4 times 10 to the negative 18 meters. All right. So what we do is, I have a little simulation, don't launch it yet, but I have a little simulation here representing what is the technique behind measuring this thing. Essentially, you build a machine that is capable, it's like a big ruler. It's a big ruler, it can measure very accurately small numbers, that's it. The machine is based on interferometry, the so-called interferometry, where at the end, what we do is we monitor, essentially, the position of two masses. See these two disks here? Let's see. One disk is over here, the other disk is over there. They actually are mirrors. They reflect laser beams, and we keep monitoring the position of these two mirrors, these two test masses, with respect to each other. So, how do we do this? Well, in the end, we launch, there's a shining laser beam, and they will bounce around. You'll see it in the simulation. Actually, Leah, why don't you launch it? What we do is we don't actually look at the position of the two mirrors, but instead we look at a so-called interference pattern at the output port, which is right here. If we notice that there's a light change, the light change depends on the position of these two mirrors. If you notice that there's a light change on that port, we know that the mirrors moved. And therefore we inferred, they moved by a little bit, therefore we inferred by how much they're moving, simply by looking at what's at this port here. Right now, for example, there is no light. The two mirrors are about to move just a little bit, and you see, and you have light. So all we do is we place our detectors, our like cameras, if you will, CCDs, to monitor what the light level is there. Because if you monitor what the light level is, you know by how much the mirrors moved. Now, mind you, this is an interferometer, very simple interferometer. One that's in place is a lot more complicated, but the idea is just the same, follows the same. This is one of them. There is the machines responsible for this detection. They are the LIGO machines within the United States. The one that I'm showing you here is at Hanford in Washington State, in the high desert. Yes, there's a high desert in Washington State. Lots of rattlesnakes, tarantulas, and all that kind of stuff. The laser is stationed here. This is the corner station. It is L-shaped, just like the microsome, just like the interferometer that I showed you before. This is one arm, and this is the other arm. At the end of this arm, you have one of these mirrors. So actually one of the mirrors receives the laser beam, bounces it back, and then the interference pattern actually receives at the corner station. The length of one arm, 4 kilometers. This is a monster of a machine. One of the LIGO machines. A twin machine. Has to be in the desert simply because we want to isolate this machine away from populations and things like that, because we want to have quiet places. But at the end, the mirrors are subjected only, possibly, to the exposure of gravitational waves. There are many environmental factors, of course, many of them. And we count them every day, and we have to chase them every day, that kind of thing. But we want to isolate machine as much as possible. The other guy is identical. It's a twin machine. It's in Livingston, Louisiana. Before there were rattlesnakes in Washington, now you have alligators here. Corner station, one tube, 4 kilometers long. At the end of the one tube, you have one of the mirrors. Tube this way too. At the end of the tube, you have also another mirror bouncing the light back. So at the end, you have an interference pattern at the corner station. So these two machines are the ones responsible for the detection. There is a third machine. Actually, you see there's a little graphic of where these two machines are, 3,000 kilometers apart. The other machine, which is part of the collaboration, is also, it was actually off at the time of the event simply because of a major reconstruction, major upgrade they were undergoing. It's called Virgo. It's in beautiful Tuscany in Italy. Very nice place to work. And the arms here are 3 kilometers long, and the corner station is still there. And the system is a little bit different from LIGO's system, but the principles are just the same. They have for example, they pride themselves in using a so-called super attenuator. That means essentially that they have, this is their test mirror. It's supposed to be exposed only to gravitational waves, okay? And they have a suspension that's about, I'm not sure how many meters high, to isolate this to the environment as much as possible. LIGO does not have this, employs different techniques. Okay, in fact, this is LIGO's isolation system, and the mirror itself. The mirror is about this big. All right. Okay, so the signal that we received, remember, the signal that we received is just a, let's see, how can I do it? You know how you listen to music using a laptop, for example, and every once in a while when you listen to music, you have the opportunity to actually look at the waveform that comes along with that sound file. It's all like encrypted and goes all over the place and so on. Well, we have a signal that's very similar to these waveforms. We have a strain signal that essentially tells us by how much the mirrors moved. And this is actually the data that was critical in the clearing detection, because At the very top here is the signal in strain detected by one of the interferometers, the one in Washington State, and that is shown in red. Okay, so at the very, very beginning, you cannot discern something, and then you start discerning some things. You see a signal that looks like periodic in nature. The frequency seems to be increasing. Okay, great. At the same time, in Louisiana measures the one in blue shown here. And if you overlap the two, they're awfully similar to each other. So that was an indication in the end that they are both registered the same thing. But that's not it. That's not the end of the story. To add on top of this is that we have friends, we have colleagues, that what they want to do, they pride themselves and they want to working on so-called numerical relativity. What they do is they take general relativity and then they say, well, what if we had two black holes orbiting around each other, coalescing to and forming a third? What kind of a gravitational wave should we have? Okay? And so they predict what kind of a gravitational wave we should have. Well, guess what? Their prediction is shown here in gray and matches to the one in red, which is essentially a soft version of the one that you see above. In an indication that the expectations coming from Albert Einstein, there's no disagreement. There's complete agreement. They lay on top of each other. So not only the two stations, 3,000 kilometers apart, saw it, but also the numerical relativity guys that work only on these things predicted we should see this. And so we did. To some degree, we are happy. To another degree, it's like we're not so happy, because if there was some sort of a disagreement, it would be great, because that means it gives you more things to think about. Or maybe I did this wrong. You go back to it. But anyway, it matches completely. That's awesome. So it gives us confidence that what we saw was a gravitational wave. This is the story for Hanford in Washington State. This is the story for Louisiana. Great. Now,